So last lesson was kind of a big lift, and we made the argument that the process that gives us the antiderivative, the process of taking integrals, also gives us the area under a curve. Awesome. Okay, but so let's step back and think about what that means. First of all, like the area under a curve, that is a number, and the integral so far has been a function. And in fact, if we remember like how indefinite integrals work, they have that plus c business, that the integral is actually a group of functions. So in this last lesson, we're going to bridge that gap with the idea of definite integrals. So definite integrals are what we use to calculate areas. And what does it definite integral looks like? Well, here's one. The integral from 1 to 4 of x squared with respect to x. Okay, so what makes it a definite integral is we've got these, what we call limits of integration. There's a lower limit and an upper limit, and those are the values on the x-axis that define the area we're interested in. Okay, so for this specific definite integral, x squared looks like that. And what we're looking at here is the area on the x-axis from x equals 1 to x equals 4. Okay, so let's make that 1, and this 4, and this is kind of the area we're talking about here. That's not the straightest of lines, but you get it. There's a much neater picture in the notes there. Okay, and so this definite integral, again, what makes it different from an indefinite integral is we're saying we're putting in lower and upper x values, and those are the lower and upper bounds of the area that we're looking for here. Okay, so yeah, I think I'm going to go to another page to do the steps and evaluating any definite integral, but the one we're going to look at here is the same one, dx. So the first step is to find the indefinite integral, okay? And again, I'm using this convention of the capital F being the integrated function. So the integral of lowercase f, in this case x squared, is uppercase f. The derivative of uppercase is lowercase. And great, we found that before. So that integral, I'm just copying my problem so that I'm staying oriented here, is x cubed over 3 plus c. Okay, we found that in the first lesson, right? And what we want to do, though, is even though this step was finding the indefinite integral, we want to carry those upper and lower limits along with us. And people usually do it with this kind of like vertical bar here. Okay, and so again, we would read this as x cubed over 3 plus c as x goes from 1 to 4. That's what we're doing. Okay, so now we are going to take that indefinite integral f at, we're going to evaluate it at the upper and lower bounds, okay? Upper and lower limits of integration. Okay, so f of 4, this is our f function, right? F of 4 is 4 cubed over 3 plus c, that is 64 divided by 3 plus c. Okay, and same thing for f of 1 for the lower limit. Okay, that's 1 cubed is 1 divided by 3 plus c, third. And the last step is subtract. Okay. F of the upper from f of the lower to get the area. Okay, so in this case, it's going to be 64 minus f of 1 equals 64 thirds plus c minus 1/3 plus c. This subtracting off this whole thing. So what always happens with definite integrals is the constants go away. You've got the same constant in both places. You take the difference, they're out of your hair. You don't need to worry about them anymore. So what we're left with here is 63 thirds, 21. Okay? That's our area. Great. And yeah, that's really all there is to it. This part of the process, if conditional on being able to find the indefinite integral, that can be hard, but in this case, we had a function that was easy to integrate. The rest of the process is very kind of, you know, fill in the blanks to get the answer there. And we will be doing some of that in probability. Some of these areas do actually correspond to probabilities of events. Okay, the final two comments I want to make. There is more to be said about finding areas with integrals. I'll just mention two of them. I'm not going to mention all of them. There is more on integration in EMEA, the Sid, Sater, and Hammond book, and as with really all of our topics, they cover the subject in greater depth. So that's a place to, if you're looking for more, it's a good place to start. But two little comments here. One is, if you're looking for the area below the x-axis, just multiply the definite integral by -1. Another way to express the same thing is if you take an integral and you get a negative number there, it probably means that the function is below the x-axis there. And so if you want the true area, just multiply by -1. Areas should be positive. I think it's pretty unlikely that you're ever going to need to do this, but just thought it was worth mentioning. On the other hand, something that I know that you're going to need to do sometimes is to evaluate integrals with plus or minus infinity on the limits. Okay, so here's one, the integral from -infinity to infinity of f of x dx. I bet you can guess what we do here. We can't handle infinity, but what do? We think about the limit as x approaches infinity of f of x minus limit as x approaches -infinity of f of x. Okay, so we can't substitute these limits into f because they're not numbers, but we can think about x getting arbitrarily large, x approaching this kind of stupid to call infinity and upper limit, but it's in that position in the on the integral sign there. So x approaching the upper limit and x approaching the lower limit there. Or sometimes you might see something like 0 to infinity. Okay, so again, we'd have to take the limit to find the upper value there. But we've got an actual value of 0 for the lower limit. Okay. That limit won't always exist, right? Because sometimes the area itself will be infinite, but there are cases where the function's getting closer and closer and closer, getting so close to the x-axis as x goes to infinity that we can actually calculate its limit, and the limit will be a finite number there. So in our workshop, we're going to look at some functions that work like this. You'll have a chance to practice that then, and we'll use that in 200 days in the fall. Okay, so Unit 7's been kind of an intense unit, but it's a set of ideas that are going to be reinforced in fall quarter. And so the work you're putting in right now, even if you're feeling like, wow, I'm just working hard, I'm so lost and confused, I'm telling you, it's going to help. Okay. Any time that you spend doing the integrals problems, trying to go over the notes, even if you feel like you're getting nowhere now, when it comes up again in a couple of months, you're going to be ahead of where you would otherwise be. And so do some problems and we'll see you in the workshop.